Hi everybody. This is part 2 of section 3.1. It's a very long section, so we wanted to break it up into parts. And this part, we're really going to be focusing on the math part of it. Because in the last half, we looked at probability, and we found that calculating probabilities rely a lot on being able to count things like count the number of outcomes in a sample space and the number of outcomes in an event. So we want to go through some counting techniques. And before we get, when everything is all said and done, yes, we will have a number of formulas, and it's going to be, might seem like a pretty complicated thing, but all these formulas really come from the same principle, which is the fundamental counting principle. And let me just, there are two versions. One, I'll give you the version that appears in your text, version 1, which says that if you have two tasks, and you know there are m ways to do task 1 and n ways to do task 2 once task 1 has been done, then there are m times n ways to do task 1 and task 2 in order. Okay? And that seems to be maybe straightforward. For example, if there are 10 boys and 10 girls and you need to choose one boy and one girl, how many ways can you do that? Well, let's say you first choose the boy. There are 10 ways to do that. And then you choose a girl. There are 8 ways to do that. Okay, so that means that would be 80 ways to do that. And, one way you could do that, another way to see that is if you have your 10 boys, say B1, B2, B3, all the way up to B10. And then for each choice, then you choose a girl, so you'd have, G1, G2, all the way up to G8. Then you do the same thing for B2, G1 through G8, and so on. Okay, and then you'd see that there are actually going to be 80 of these nodes, these final nodes here, where each node represents a way you can do this task. Okay, so hopefully that seems to be kind of apparent why we're multiplying and we're not adding, right? Now, a much simpler way, maybe smaller numbers, is if you want to, make a peanut butter and jelly sandwich, you first choose your peanut butter and then you choose your jelly. Well, let's say maybe you also have to choose your bread. Well, that would be a case where you have 3 tasks to do. So we need to generalize this fundamental counting principle. And it says, let's say you can break a task into k subtasks, or let's say you have k tasks to do in order. And there are m sub 1 ways to do task 1, there are m sub 2 ways to do task 2, m sub 3 ways to do task 3, and so on. And then m sub k ways to do the final task, task k. And let's say you're doing all of these in order, okay? So then there are going to be the number of ways to do all these tasks in order would be just the product of all these m's, m1 times m2 times m3, all the way to m sub k. Okay, so this is the fundamental counting principle. It's also sometimes called the multiplication principle for the obvious reason, right? Because you're multiplying all these numbers together. So just to do a bunch of examples, the best way to learn how to do this is a lot of examples. So let's getting back to the concept of peanut butter and jelly sandwiches. Let's say if you have 3 types of peanut butter and 5 types of jelly and 2 types of bread. Well, first you choose your peanut butter. There are 3 ways to do that. Then you choose your jelly. There are 5 ways to do that. And then choose your bread. There are 2 ways to do that. So 3 times 5 times 2, that would be 30, right? And again, just to see how this works, here's your peanut butter, P1, P2, let's say these are your 3 brands of peanut butter, and then you have these 5 brands of jelly, Okay, so let's say here's J1, J2, J3, J4, J5. Okay, and then for each jelly, for each choice of jelly, you're going to have you choose. After you do that, you have two types of bread to choose from, right? So again, once again, you have all these nodes here, and that corresponds to, you know, the number weighted to make the number of possible sandwiches. So it'd be 3 times 5 times 2. That's 30. Okay. So let's do a few more examples illustrating this. All right, and this is going to be a little bit we'll be approaching that from a different perspective. Let's say the number of pizzas available if there are 8 toppings available. So we just worry about the toppings and what are the ways you can do that. Okay, now the way to do that is kind of an unusual way. But let's say when you order a pizza at this place, you're implicitly making 8 decisions. Do I want this topping? Do I want this topping? Do I want pepperoni? Do I want, mushroom? Do I want onion? And the answer is either yes or no. Okay? So there are these 8, behind every order there are 8 yes or no questions you have to answer. And then you just say, and then that completely makes up your order. Okay? So, so the way to do that is, so in a typical order, you're just going to be saying, here are eight possible toppings. Okay, so topping 1, topping 2, topping 3, topping 4, and so on. Okay, and let's say I want topping 2 and topping 4 and topping 5. Okay, and I don't want any more toppings, so I'll just put in an X here. So basically, every order corresponds to some way to fill this out with X's and checks. All right. Okay. So now, how many possible ways can we do this? Well, we fill out this first one, or for topping 1, we're either going to have it or we're not. So we're either saying yes or no. So there are 2 possibilities for topping 1. Topping 2, again, 2 possibilities, yes or no. Topping 3, 2 possibilities, yes or no, so on. And then 4, 5, 6, and 7, and 8. Okay? So therefore, then this is going to turn out to be 2 to the 8th power. Okay? And which turns out to be 256. And yes, you can use your calculator to do this. I don't expect you to do this in your head. Okay, but that's the way we do this. And in fact, I don't know if any of you are old enough to remember how Wendy's used to take your order. They would have all these toppings listed, and basically it would record your order like this. It would just put a check. They wouldn't put an X's, but they would just put the checks in front of the toppings you wanted. Okay. And you can guess that, for 9 toppings, there would be 2 of the 9th possible pizzas, and so on. All right, about another example. Let's say the number of different outcomes of tossing a coin 10 times. Well, it's kind of the same thing. You what are the possible outcomes of this? For each toss, there's only 2 outcomes, heads or tails, right? So we would basically... the result of a trial would be something like this, tails, tails, heads, heads, tails, heads, tails, heads, and let's say tails. Okay, so we can describe each outcome like this as a sequence of 10 symbols where they're either heads or tails. Okay, so once again you can say, okay, well here are 10 possibilities. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we'll forget this. So once again, there are 2 possibilities for the first. 2 possibilities for the second. Your third, fourth, fifth, sixth, 7th, 8th, 9th, 10th. So it's actually going to be, there are 2 to the 10th possible ways you can fill this out. using heads or tail, H's or T's. And so this is going to be 2 to the 10th, which is 1,024. Okay, so there are 1,024 different outcomes if you toss a coin 10 times. Another variation on this, the number of different outcomes from tossing a coin, rolling a 6-sided die, and choosing an integer between 1 and 20. Okay, so basically we're doing here we have, instead of 10 tasks, we have 3 tasks. The first is basically recording the outcome of a coin toss, then recording the outcome of a dice roll, and then recording the integer that was chosen. Okay, and let me remind you, the integers, how many integers are there between 10 and 20 inclusive? There are actually 11, right? Because you have 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20, right? So there are 11 choices there. So there are 2 choices, or 2 possibilities for the coin toss. There are 6 choices for the 6-sided die, and 11 choices for the integer that was chosen, right? So this would be 2 times 6 times 11, which is 132. Right? And basically, again, you can think of this, recording the outcome. Here's one for the coin, the die, and the integer. Okay, the 2 goes here, 2 choices here, 6 possibilities here, 11 choices here. All right. Let's look at the next example where we're counting the number of 5-digit numbers. Okay. Now remember, 0 is a digit, so we're counting, even if the first digit is a 0, we're counting that as a 5-digit number. So a 5-digit number has 5 digits, right? 1, 2, 3, 4, 5. So you can think of a 5-digit number as just a collection of 5 digits right here, a list of 5 digits, in which order matters. Okay, so how many 5-digit numbers are there? Well, it's easy. There are 10 choices for the first digit, 10 choices for the second, 10 choices for the third, 10 choices for the fourth, 10 choices for the fifth, right? And this turns out to be 10 to the 5th, which is, I believe it is 100,000. So there are 100,000 5-digit numbers. Now, let's say what happens if we add some modifications, some qualifications. Let's say we wanted to count the number of 5-digit numbers with no 4s. Okay? Well, if there's no 4s allowed and everything else is allowed, then there are 9 choices for the first digit, 9 for the second, 9 for the third, 9 for the fourth, 9 for the fifth, right? Because we can have any digit except 4. So this would be 9 to the 5th. And then this turns out to be 59,049. Okay. Now, with these 2 numbers here, we can answer our next question about how many numbers with at least 1 4. Because either this number is going to have a 4 as a digit or it's not. And we know that this many do not. And we know this is the total number of 5-digit numbers. So to find, this and this event and this event are really complements of each other. Okay. Okay. So what we do is we know that there are 100,000 total. We know 59,049 have no 4s. So that means 100,000 minus 59,049, those must have, they must have at least 1 4, right? So when you kind of compute this on your calculator, this is 40,951. Okay, so 4. Let's see, what's next here? 5-digit numbers with no repeated digits. Okay, so if I asked you, okay, give me a 5-digit number with no repeated digits, and you start picking your digits, the first digit can be anything you want, so there would be 10 possibilities for the first digit. The second digit can be anything except the first digit, so there would be 9 possibilities there. The third digit can be anything except the first and second digits, which are distinct, right? So there would be 8 possibilities for the third digit, and then there would be 7 possibilities for the fourth digit, and there would be 6 possibilities for the fifth digit. Okay, basically you're just you're eliminating all the digits you've used so far. Okay, so this would be 10 times 9 times 8 times 7 times 6, which turns out to be 30,240. All right. What about the number of 5-digit numbers where the last digit is odd? Okay. So the last digit is odd. There's no restrictions on the other digits. So there would be 10 possibilities for the first digit, 10 possibilities for the second, 10 for the third, 10 for the fourth. And then since the odd digits are 1, 3, 5, 7, and 9, there are 5 digits, so there are 5 possibilities for the last digit. Okay, so this would be 10 times 10 times 10 times 10 times 5, which is 50,000. All right. What about the number of 5-digit numbers where the first digit is even and there are no repeated digits? Okay. If the first digit is even, remember the even digits are 0, 2, 4, 8, 6 and 8, and 6. I didn't put those in order, but there are 5 of them, right? So there are 5 choices for the first digit. Now, the second digit can be anything except the first digit, so there are 9 possibilities for the second digit. The third digit can be anything except the first 2, so there are 8 possibilities for the third, and then there are 7 possibilities for the fourth, and there are 6 possibilities for the fifth. Okay, so this is 5 times 9 times 8 times 7 times 6, which is 15,120. Okay. And then finally, the number of 5-digit numbers with at least 1 digit repeated. Well, this is the complement of this with no repeated digits, right? So there are this many ones with no repeated digits, and there are 100,000 total. So again, this would be 100,000 minus 30,240, which is 69,760. Okay, so the best way to do this is get lots and lots of practice, do your homework. We'll do some more examples probably later in some other videos. But please get started on this and have a great day.